Hey guys, sorry for the delay in getting this video out. It was because I was looking through the Action Center over the week, and I realized that most of the questions were just super formulaic, and it was just, you use the Michaelis-Menten equation, you plug in the numbers, and you get some answer. But I know that enzyme kinetics is a super hard topic to conceptualize, and it's really hard to wrap your head around what's actually going on when you start doing it. And so what I wanted to do in this video was to actually derive the Michaelis-Menten equation, show you how it works, the assumptions that we're making to make the equation work, and I'll also show you how to do Lineweaver Burk plots, because that's also really important for when you start talking about inhibition types, which will be the video that I make next week. And so I know that you've probably seen the Michaelis-Menten equation derived with calculus before, and so I'm going to show you the method that I use to derive it, which doesn't use calculus. So it was just how I understood it when I was taking the class, and so I wanted to show you guys how to do that. And so the way that I start doing this is I write my enzyme equation. So it's enzyme plus substrate. This is reversible. And we go to the enzyme substrate complex, and then this irreversible arrow to get to enzyme plus product. And this is irreversible just because we can assume that, the enzyme and product isn't going to sort of reverse itself back into the enzyme plus the substrate or enzyme substrate complex, just because, it'd be so energetically unfavorable to do so. So we're going to call the forward rate here K1. We'll call this dissociation K2, and we'll call this K3. Now, to actually do a derivation of the Michaelis-Menten equation, or to have the equation work in the first place, we're going to make two assumptions. The first one being that we're going to assume that the substrate concentration we have is much, much greater than the enzyme concentration we have. And the second assumption we're going to make is what we call the steady state assumption. And what that means is that the rate of formation of the enzyme substrate complex, that's going to be equal to the rate of the loss of the enzyme substrate complex. And that sentence of, rate of formation of the enzyme substrate complex is equal to the rate of loss, or just the steady state assumption, those are words that are going to be thrown around. And it's very helpful to understand, conceptually what that means. And so essentially what it means is that if I draw a little graph here, and if I put concentration here versus time, so my substrate's going to go down over time. We'll call this the substrate concentration. At the same time as the substrate concentration goes down, the product concentration is going to go up by the same amount. While the product concentration goes up, you've got two things happening, one with your enzyme substrate complex and one with your free enzyme. And so what happens there is you get this sort of, it almost looks like a hyperbolic curve kind of thing. So two things happen here, where your enzyme substrate complex and your enzyme there's a period of time where these rates of change are going to be exactly the same. That's the steady state assumption, meaning that, while this reaction is happening, while enzyme is being converted to the enzyme substrate complex, and then that's being converted to an enzyme and a product, the enzyme substrate complex and the enzyme concentration, like the free enzyme concentration, are going to remain the same the whole time. So that's what the steady state assumption is. And so that's going to set up the first step in our derivation. So if we consider the rate of formation of the enzyme substrate complex, we look back here at this equation. And so the only thing that contributes to the rate of formation of the enzyme substrate complex is this rate here, K1. So I'm going to start with K1, and that's equal to the rate of loss of ES. So the two things that take away from the ES concentration are K3 and K2. So K1 is then equal to K2 plus K3. So that's our first step. And now we'll start writing these out as actual rates like you would in general chemistry. Like when we say that, if we're looking at E plus S going to ES, the ES complex, we would say that our rate there is K1 times, the enzyme times the substrate concentration. That's like the rate equation for that rate constant. And so that's exactly what we're going to do here. So K1 is going to be equal to K1 times E times the substrate concentration. And then K2, let me move this down here so I can see it while I do the... Okay, so then K2 is going to be equal to K2 times the ES complex, because that's the only reactant there, plus K3 also times the ES complex. And now we're going to make another assumption here. We're going to say that the total enzyme, E total, that's going to be equal to the free enzyme plus whatever's in the ES complex. That should make sense because, the total enzyme we have is going to be the free enzyme plus whatever enzyme is actually doing something. And so if we manipulate that equation around a little bit, we can solve for E because that's what we actually have in this equation. So then E is going to be equal to the total enzyme, I'm just going to call it ET, minus ES. So then we can plug that back into the initial equation. So then this becomes K1 times the total enzyme minus the ES complex times the substrate is equal to K2 times the ES complex plus K3 times the ES complex concentration. Now what we're going to do is we're going to distribute out that term that we have in the left-hand side of our equation. So we'll get K1 times enzyme, the total enzyme, times the substrate, minus K1 times the ES complex times the substrate equals K2 times the ES complex plus K3 also times the ES complex. And I know it just seems like a lot of algebra right now, but I promise it has a point. So now what we're going to do is we're going to say that K1 times the total enzyme times the substrate minus K1 times the ES complex times S. That's going to be equal to, we're going to factor out the ES here, so ES times K2 plus K3. And then now we've got these two K1s. So we're going to divide each side of the equation by K1. What that's going to give us is, so this right here, this is really important, K2 plus K3 over K1, this is the definition of Km, that constant. So we can rewrite this as the total enzyme times the substrate minus the enzyme substrate complex times the substrate, because the K1s would have canceled out there. This is going to be equal to Km now times the enzyme substrate complex. So now if we do a little bit more algebra, we're going to try to isolate the enzyme substrate complex, because the concentration of the enzyme substrate complex is initially going to lead us to our velocity of the reaction. So we'll say that, the total enzyme times the substrate is equal to Km times the enzyme substrate complex plus ES times S. And then we can simplify that even more. We'll factor out the enzyme substrate complex here. We'll get Km plus the substrate concentration. So then our last step, we can say that the enzyme substrate concentration is going to be equal to the total enzyme, ET, times S divided by Km plus the substrate concentration. And this bottom half of the equation, now this should look a lot like the Michaelis-Menten equation. Now, what we want to find is the rate that the product is being made with respect to time. So we want this, I'm going to write it as this derivative because that's just technically correct, but all this means is that we want to find the rate of change of the product over the change in time, or with respect to the change in time. Now, what that is we're saying that this is K3 times the enzyme substrate concentration. Because if we go back to our initial equation here, the rate that this product is being formed is this rate K3. So if we were to write that as an equation, it'd be K3 times the enzyme substrate complex. So that's where that comes from. And we also know that when the substrate concentration goes to infinity, then velocity of our reaction goes to Vmax. And we know that because if we look at a Michaelis-Menten equation, or a Michaelis-Menten graph, sorry, if I have V naught here and I have my substrate concentration here, if we increase the substrate concentration, this gets closer and closer to our asymptote at Vmax. So that's how we made that assumption. And then we can make one more thing. So we can say that at Vmax, the enzyme substrate complex, we can assume that that's going to be equal to the total enzyme. Because if our reaction is running at Vmax, then our enzyme is going to be fully saturated. So with that in mind, we can say that K3 times ET, the total enzyme, equals Vmax. And that's a combination of, these two pieces of information that we just got. So we can rewrite this equation as K3 times the enzyme substrate concentration. That's going to be equal to K3 times the total enzyme times the substrate concentration over Km plus the substrate. So this, if we simplify that, we get our Michaelis-Menten equation. So K3 times ES is going to be the rate. So whatever rate we're operating at will be V naught. That's going to be equal to K3 times enzyme, the total enzyme, which we know is Vmax, times the substrate concentration over Km plus whatever substrate concentration we have. So that's how you get this Michaelis-Menten equation. And you don't need to know how to do that necessarily. Like, he's never going to ask you to, derive it out on a test. But I hope it was helpful in just, rationalizing the fact that there is more to this than it's just, memorizing this formula. You want to understand, what a steady state is, how Km actually relates to these rate constants, what the rate constants mean, you know, why does the enzyme substrate complex equal the total enzyme when we're at Vmax, those kind of things. Now, if we want to define what Km is, we can say that, we can say if Km equals the substrate concentration, then V naught is going to be equal to Vmax times Km over 2 Km, because we just plugged it in to this bottom part of the equation. We got 2 Km. So these Km's would cancel out, and we're left with V naught is equal to Vmax over 2. So that's essentially that's like a proof of saying, so when the substrate concentration equals Km, the reaction runs at half of max velocity. And graphically, what that's going to look like is here's V naught, here's our substrate concentration, and there's our curve. This is Vmax. And when it's running at half of Vmax, the substrate concentration that we're at this point, that is Km. All right, and so, once we know Km, you should also know this equation. So a measure of catalytic efficiency. Catalytic efficiency essentially, it depends on how well the enzyme functions as a catalyst, depending on how avidly it's going to bind its substrate. And the measure of affinity that we use is Km, and how rapidly it converts that to a product, which is Kcat. So, or, K3. K3 is also called Kcat. So the way of writing that in the formula that you should know is Kcat over Km. And, Kcat is K3. And so that's always going to be your measure of catalytic efficiency. And so the upper limit for that, because this is a second order reaction, the upper limit is going to be 10 to the 8th to 10 to the 9th per molar per second. And so whenever he asks you to calculate catalytic efficiency, you're just going to use that formula. And you're going to say, like, if he asks you, is this reaction working at catalytic perfection? You see if it is in this threshold or higher than that threshold. If it falls into that, then it is at catalytic perfection. And if it's below, like if it's 10 to the 7th or something, or lower than that, it wouldn't be. And sometimes that's called diffusion control as well. So he might say it like that. Catalytic perfection and diffusion control essentially mean the same thing. Now, before I get into Lineweaver-Burk plots, I do want to mention that there are some exceptions to the Michaelis-Menten equation, and so it cannot work with, it can't work with the following. So, number one, multi-substrate reactions. Number two, multi-step reactions. And number three, non-hyperbolic reactions. So these are things that are like allosteric, cooperative things. So like, hemoglobin, you're never going to be able to be asked a question about hemoglobin in the context of a Michaelis-Menten equation because it won't work. And so just keep that in mind when you're doing these questions. I think it's highly unlikely that he will ever ask you to do something like that just as a trick question and have you say like, oh, it's not going to work because it's one of these, but it's just something to keep in mind that it's not going to work all the time. It won't work for every single enzyme. And so the next thing I want to do, the last thing actually, is talk about Lineweaver Burk. And I'll show you how to derive that equation. So let me grab this and put it down here so that I can reference it. And I just lost it. Okay, great. All right. So that's what our normal Michaelis-Menten graph looks like. And when we talk about enzyme inhibition, it's really hard to talk about enzyme inhibition with one of these just because of the way that they look. It's hard to tell what kind of inhibition is going on just from looking at a regular velocity graph. So what they did is these two guys, they came up with this double reciprocal plot, which we call a Lineweaver-Burk plot. And the way they do that, it's called a double reciprocal plot because you basically take the reciprocal of the Michaelis-Menten equation to get that equation. And so here's our normal equation. V naught is equal to V max times the substrate concentration over Km plus the substrate. So if we take its reciprocal, we'll get 1 over V naught is equal to Km plus substrate concentration over V max times substrate concentration. And then we can split this up into 1 over V naught equals Km over V max times substrate concentration plus substrate concentration over V max times substrate concentration. That's just how fractions work. You can do that. So these substrate concentrations will cancel out over here. We're left with 1 over V naught is equal to Km over V max times 1 over the substrate concentration. I just pulled this out of the denominator here, plus 1 over V max. And the reason I pulled it out is just so that it takes the form of the equation y is equal to mx plus b. Now, so we know that our y-intercept is going to be b, so this is our y-intercept, 1 over v max. And so to solve for our x-intercept, we'll set the y value equal to 0. So 0 is going to be equal to Km over v max times whatever x-intercept we're at plus 1 over v max. So negative 1 over v max, I subtracted that, is going to be equal to Km over v max times the x-intercept. And so we do that division, we'll get x is going to be equal to negative 1 over V max times V max over Km. So these V maxes will cancel out, and we'll get our x-intercept at negative 1 over Km. And so using that information, we can draw a Lineweaver-Burk plot. So because our initial axes were V naught and substrate concentration, our y-axis here will be 1 over V naught, and our x-axis will be 1 over substrate concentration. And so our y-intercept we know is going to be 1 over V max. Our x-intercept is going to be negative 1 over the Km. And the slope of the equation is going to be our m here, which is Km over V max. So I hope that made some sense, and I hope it clarified some things about this topic. The more time you spend doing it and the more time you spend looking at this will help a lot. I would practice, especially like focusing on this type of logic, just the steps that got me from here to here, and like eventually the actual equation. The logic that got me there, I think, is really helpful to understanding this concept in general, and just how to derive a Lineweaver-Burk plot, like what it actually means, what the significance is. And a lot of that you'll understand, when you do inhibition, I think, is when this actually all sort of ties together. So if you liked this, style of me talking about, how to think about these problems rather than just like me plugging in numbers, let me know, and I can do another one of these for next week.